Okay, first of all, like I wrote here, I'm using Microsoft Whiteboard because I haven't found anything better. I don't know what other people use. If you have a suggestion for a board app or whatever that I could use that would be better than this, then please let me know, either in the comments or on Twitter or whatever. Anyway, we've got two more robustness facts to prove, and I'm definitely going to put less effort into kind of showing you the nitty gritty of the proofs of those than I did of the alphabet proof. And the reason for that is twofold. One, it's because one, I've already shown you some nitty gritty. We're starting to get more comfortable with this stuff, I think. And two, the remaining robustness facts, unlike the alphabet size proof, don't kind of imply anything intrinsically about the classes of languages that we're going to be talking about themselves. Because remember, I mean, it doesn't seem that way right now. It doesn't seem this way right now, but it will later. The model of computation themselves, Turing machines, are not the central concern for us. They're a means to an end. What we're interested in studying are the languages themselves, the decision problems. We want to classify them, and the Turing machines are going to help us do that. But that's the extent to which we care about them. So uh, I felt like I had to put a lot of explanation into the alphabet one, in the alphabet fact, because it implies something. It implies a standardization of the class of languages, whereas the remaining stuff doesn't really say anything about the languages. It's just developing the model. So anyway, uh, also in the last video, we talked about kind of the necessity or importance or significance or whatever of these two symbols. These two symbols that we've agreed will always be uh, in any Turing machine. And we kind of pointed out that this one is extremely necessary. This is a special symbol. You always need something that functions as a blank symbol because the Turing machine has infinite tape. And so there's always implicitly one symbol that appears infinitely often on the tape. And so you always need a symbol to function as a blank. On the other hand, this triangle is something that we agreed will be standardized in the sense that it kind of functions as the place to point when the machine starts. So in general, you have a starting tape configuration that looks like this, where the arrow is pointing at the triangle. This is our standard input method, but it's unnecessary, right? If x is equal to x1, x2, dot, 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 xn, then I could just, I could start like this, where I have the triangle here and the guy pointing at this, but I don't need that. I could just as easily just have the convention that the string x goes somewhere on the tape that I'm deeming 0. Whoops, and then the triangle is right here. Just have the triangle start on the first symbol of x. So this triangle is unnecessary. So you might question why it's there. The reason why it's there is really no reason why it's there. It's kind of, I mean, we've seen that it's kind of helpful to have a symbol like the triangle, and that's why I kept it. But it's really for a two-way infinite Turing machine, for a Turing machine whose tape extends infinitely in both directions. This triangle is actually not necessary. But for a Turing machine whose tape only extends infinitely in one direction, we're going to see that it kind of is helpful in defining that as a special case. So let's see that now. So I'm going to define a one-sided Turing machine. And I'm going to define a one-sided Turing machine specifically as a generalization of the Turing machines that we've already defined. Some textbooks start with this and then call the two-way Turing machine a generalization. I tend to go in the opposite direction because I think that the more natural model is the two-way infinite tape, in the sense that to generalize Turing machines to their quantum Turing machine counterpart, you do need two-way infinite tape. So that's kind of why I tend to think of that as the more natural one. But here's a definition that we'll only really use insofar as proving something. Um, a I don't know what to call it. A unidirectional, I guess, or Turing machine is a machine, obviously. M equals sigma, and sigma is going to be our standard, right? It's going to have our blank symbol. It's going to have our triangle symbol. Such that the convention is going to be, well, basically the idea is that we don't want to be able to go to the left. We don't want to be able to go to the left anywhere past the triangle, right? And so to do that, we just basically impose some restrictions on the triangle symbol itself. So basically, we say such that um, if delta of sigma q, or sorry, of triangle q is equal to sigma q prime d, then, well, what do we want? We want to be able to say that d obviously needs to be not -1, right? And then also we want to we want to never erase this, so we never forget that we can't go to the left. So basically, what we need to say is that then sigma equals the triangle. In other words, I cannot erase triangles once I've printed them, and d is not equal to -1, so I can't go left. So under these conditions, I think it's clear that I effectively virtually have tape that only extends infinitely to the right and not to the left. Now, you might have noticed I've never actually really used the space to the left, and really, I won't use it very much, but it's still going to be important. It's still kind of important to address this. So hopefully you see that this is uh, the definition I'm looking for. So here's a fact. Here's a robustness fact. Um, for any Turing machine, M, there is an equivalent Turing machine, M prime, which is unidirectional. And what I mean by equivalent is that M prime accepts all the same inputs, accepts and rejects, / rejects, all of the same inputs, spits out the same outputs. I'm going to put an asterisk here. With no time and space loss. And I'm going to put an asterisk here. There's a bit of a confusing little complication, but in any case, I'm not going to prove this rigorously. You can find a rigorous proof in my notes, which are always linked in the description. I'm just going to kind of talk about the idea. So we have a Turing machine that might go to the left of the triangle, and I want to describe a new Turing machine that I've built out of that never goes to the left of the triangle. So we're going to make a couple assumptions. So there's an easy way and a clever way to do this, and we kind of need to talk about the clever way. But the easy way, the obvious thing to do, is sort of so obvious that I feel like I would be remiss not to talk about it. So first of all, let's note one thing. Replacing. So there's kind of two things we need to do based on this definition. We have a Turing machine. We want to make sure that the triangle is never deleted, and the direction is never -1. This task, making sure that the triangle is never deleted, is very easy. Can easily assume triangle is never deleted by just adding in a new symbol to function as the triangle. By the last robustness fact, we can always add in a new triangle symbol, right? So I could just kind of add this guy triangle bar to be the thing that's never deleted, to be the thing that only appears right here. And then just where if I was actually planning to use these somewhere else, like put one of these guys here, then I would be able to delete it because this thing is functioning as the actual triangle. So I can always just drop a new symbol in to function as triangle if I'm actually using it. So this condition, making sure that the triangles are never deleted, that's the easy part. And so I'm not even going to bother to really talk about it. What I will say is, so like here's the obvious way. And for the obvious way, I'm going to assume that the original Turing machine that I started with is not, kind of using our standard method, but it actually um, uses this kind of input convention where there's no triangle at all. It's just easier to think about that way. So we're going to start with this input convention. And so this is the thing that I never want to go to the left of. So let's say that I were to go to the left. Um, Nonetheless, I would put a little triangle here to begin with. Um, but I want you to keep in mind that this triangle wouldn't be here for the original machine. So this is the thing I can never go to the left of, but it wasn't there as the input convention originally. Um, but the idea is um, that whenever I encounter this, whenever I need to do this, instead, oh my God, use our space creating subroutine. And what that'll produce is it'll produce tape that looks like this. It'll make a single blank, and then it'll have the normal stuff. And so because of that, it'll be as if I had moved to the left. I'm just kind of, instead of having two-way infinite tape, I have like a one-way tape where I just kind of make space that kind of pretends to be, right? So I'll just always have this triangle here, and I just, instead of going to the left, I just move everything over. That's the idea. So our space creating subroutine sort of proves by itself that unidirectional Turing machines are just as powerful. However, the issue is that if I want to, in the worst case, I would have to use the space creating subroutine every single step. The worst case would be basically that the triangle moves left every single step. In which case I would have to move the entire string to the right every single step, and that would be O of n as an algorithm. That would happen in time O of n. If you go back and look at the subroutine, you can see that that's the case, meaning that every step I'm doing a number of steps that's equal to the length of the string, meaning that I am simulating the original machine M, but I'm doing it in time O of n times f of n, where f of n is the original operating time of the new machine, and that is not necessarily O of n. In fact, it's never going to be O of f of n. So this works. This proves that at least they're just as powerful in terms of what they can compute. But this isn't actually good enough as an efficiency algorithm. We need to be more clever in order to not lose time. So the clever thing to do is what I want to talk at more depth about, at a little more length about. So what's the idea? So here's the clever method. And I'm really not sure how much I want to talk about this. Again, the proof is in the notes. There's a rigorous proof of this in the notes. So because of that, I'm not going to think too hard about it. But the idea is to take the tape, and just for simplicity, I'm going to put a positive side. Oh, I'll put a triangle here. We've got a positive side and a minus side. And so what we're going to do is we're going to take this and fold it in half. Fold the two-way tape in half, and interleave. Actually, I'm not going to put a triangle here, but we will have a single symbol here, but it's only there kind of to do something. But interleave the pluses and minuses. So basically what we get, I'll kind of do this in two steps. So I've taken this positive side of the tape and this negative side of the tape, I folded it, and then, so here's kind of step one of the folding process. I'm starting to fold it here. So here's kind of the one cell that kind of marks the in-between, and then this is all plus stuff and this is all minus stuff. And then what I'm going to kind of think about is I have tape like this. This is a one-sided tape now, but I kind of alternate. Plus, the first cell is going to be a plus cell. The second cell is going to be a minus cell. The third cell is going to be a plus cell. The fourth cell is going to be a minus cell. If you've actually ever seen the proof that the number of that the cardinality of the natural numbers is the same as the cardinality of the integers. It's kind of the exact same idea, is that we're just kind of counting them by saying, okay, this does give me all of the positive and negative cells in the same way. It's just kind of, I have kind of a plus section of the tape and a minus section of the tape. And so basically what's going to happen is um, we add in new states. So to give the machine a polarity kind of. So basically, if you have if Q is a state of the original machine, then I'll have like a Q plus and a Q minus. I'll have like a positive and negative. Basically, what the plus and the minus tell me is they're like kind of the mode of the machine. Am I moving around in the positive side of the tape, or am I moving around on the negative side of the tape? And so I have kind of two operating conditions. I have like a copy of Q, two copies of Q in the new machine. So basically, if I'm in Q plus, then what's going to happen is that I'm gonna skip every other cell. Um, so I mean, if you read the proof, I'll also have to add in some intermediary steps. But basically, if I want to change something about this cell and then move to the right, if the original machine is doing that, then instead my simulating machine will move two steps to make sure that it's always looking at positives. And same thing with the minus. It basically will make sure to always have the cursor skip a cell so that so when I'm in the plus mode, I'm only operating on plus cells. When I'm in the minus mode, I'm only operating on minus cells. So we're skipping every other cell to stay on the plus side. Similar for minus. It's a little more confusing for the minus side because on the minus side, if I'm moving to the left, then that actually needs to correspond to moving to the right over here. So it gets kind of confusing. If you read the proof, you'll see that my directions are always flipped around when I'm describing the minus states or the minus transitions. Um, what else do I need to say? Oh yeah, and then finally, basically what's going to happen is that whenever we have the cursor here and are moving to the left or the right, if cursor is on a triangle, and again, I'm going to make sure to add another symbol if I need to, such that this triangle is never anywhere except for right here. So if my cursor sees a triangle, it knows that it's either going to that it might have to change modes, right? So if I see the triangle and the direction is to move left, um, then I know I'm going to be on the negative side of the tape for a while, so I need to switch into my minus state. And then if I'm going to go to the right, I need to go into the plus state. Then we'll need to possibly change modes, change polarity to reflect the side of the tape being operating on. So that's the idea. So basically, you just kind of fold the tape on itself. You interleave the positive and negative side so that it's all on one side. And then you have two operating modes, plus and minus, that you'll switch between depending on what side of the tape you're actually simulating. And you make sure to hop and skip so that you're always kind of staying on the plus side or the minus side. So that's the clever way to do it. And a quick inspection of this will reveal that there's no increase in the time required. Asterisk. There's one little issue with this, which is that suppose that my original machine operates on a string x. The input convention will look like this then. I'll have kind of an x1, x2, x3, dot, dot, dot. This is the original machine. I should probably put the tape extending to the left just to reflect that. So suppose this is the original machine's input string. What does it need to be for the simulating machine here? Note that these are all on plus side is the convention. And so that's a bit of an issue when my plus side is like wonky like this. So we'll need to start m prime in looking like this. It'll have to kind of look like this, where I have x1 and then a blank, and then x2 and then a blank, and then x3 and then a blank, dot, dot, dot. I'll need to put a blank in between every one of these. Now, that is a bit of an issue in the sense that I kind of have to use my space creating subroutine. The fastest way that I can think of to do this is to move the cursor all the way over to xn, and then use my space creating subroutine right here, move xn over, and then keep doing that working back. And if you think about the number of steps required to do that and to configure the initial string to look like this before running my actual simulation, it's going to be like O of 1 plus 2 plus 3 plus 4, because I need to move this guy over 1, and so that's like a string of length 1 that I'm doing my subroutine on. Then I'm doing my subroutine on a string of length 2, a string of length 3, so it's like dot 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 plus n. So it's like 1 plus 2 plus 3 plus 4. That's kind of how many steps that's going to take. And if you're familiar with this pattern and all, this is the triangular numbers. And it's a lot, in fact, it's a lot like the integral of n. But it's basically, it's actually, the formula for this is O of n times n minus 1 over 2, which is O of n squared. So we didn't actually make it faster just because of this input stuff. But you know, that this is kind of a bit of a lesser kind of issue, right? Because I could just initiate it right like this. That could just be the convention. Now that's not a satisfying reason. The best answer I can give is that remember that the convention for analyzing space complexity is to use a Turing machine with input and output. Remember, when I was thinking about space, I was going to actually be only thinking about Turing machines with input-output strings. So basically, 3-tape Turing machines that look like this, where I have my x up here, and then I have a work tape. This is the input tape. And then I also have a write-only output tape. And remember, the write-only output tape is special in that I can't ever move left. So I don't have to worry about being on the left side of that tape. So this is kind of the convention for space complexity, but you know, we should probably also make this the convention for time complexity. And if that's the case, then I don't have to worry about this issue of the input, because the input's just going to be up here. I'm never going to move left of I'm never going to move left. Like, it's easy to imagine that I'm never going to need to move left of the input because it's write only. And then I can just make sure to be doing whatever I'm doing on the work tape. And the work tape doesn't need to be initially configured, so this algorithm works. At worst, this algorithm takes 2 steps for every step. So it's O of 2 times f of n, which is still O of f of n. And I don't lose any time complexity as long as I start the input on a special tape, which I was already going to do for space complexity, but I guess now we're going to do it for time complexity also. The reason it's not that bad, even then, you know, I'm not super comfortable doing this. But the bottom line is that O of n is just kind of too simplistic of a class. This class is really, well, that's not really the reason. I guess we just need to assume that we're always going to be working with the convention that when analyzing complexity, when analyzing resources, and not just what's computable. I think this is probably the best thing to look at: this input versus output, this input-output model, where you have a special string for the input and a special string for the output. And as long as you're thinking that, then none of this stuff I set up here matters. and this algorithm works just fine. Uh, and then, of course, there's also no space loss, right? I mean, I'm not using any extra space. I'm just rearranging the space. So the space and time are the same, and that's the trick. So that is our third and almost final robustness fact. The next one we have to do is show that multiple tapes don't matter. So I can take a k-string Turing machine, like this 3-string Turing machine, and always collapse it down to a 1-string Turing machine. Although there will be some time loss, and that time loss will be exactly this. So we'll talk a little bit about that. So see you in the next video.